on yet. Okay, now I got it on. All right, there we go. So, so question number 4 is going to be answered along the way. Okay, so what we'll do is we are going to shift our attention to the processor. And I got a few questions about PC, the program counter. You just have to look closer. I mean, it is here somewhere. Okay, it's right here. The program counter is right there. It is just abbreviated as PC, which is the name that I used in the question 2. So for the most part, this lab does require people to kind of go through a little bit like, where in the world is, I think it's Carmen Sandiego, and also a little bit like, where's Waldo, and a little bit like, solving a puzzle, which is question number 4 of the lab. So we'll get to that part. So what we'll do today is to look into the mechanism to move something from, well, I would just say between the registers and RAM. Okay, this is RAM. We talked about this in the previous class. All right, so Aiden types, okay, there are a few text traffic here. Is the value in the other PC the same? Well, one is in binary, the other one is in hexadecimal, so they are the same. And you know that they are the same because when you look at the wire, okay, if you click on the wire, you can see that the output of the program counter, which is also named Q, okay, we should be fairly familiar with the output Q because of the discussion of D flip-flops, right? So the output of this register PC does go to this particular output pin. So the output pin is really just a way to represent what is inside the program counter. Okay, so that's basically the relationship between the register and the pin that is also named after the program counter PC. All right, so getting back to what I was mentioning, right. So I was trying to mention, how do we move things between the registers inside the register bank and RAM? Okay, in other words, okay, I'll use an example. Let me see which one I should use first. Reading is easier, so let's go ahead and try to read a byte from RAM and put it into a particular register. So I'm just going to write on the side somewhere. Okay, so let me get my little post-it note here, get a new page on my little post-it. Okay, it's not letting me do it, which is strange. I can only have 5 pages. Oh, nope, I got a new one now. There we go. So this is my little post-it, and we'll say we want to copy. Okay, that's not showing very well. There we go. So we want to copy the content at location 0x, I don't know, let's just pick 17 to register B. Okay, so that's all we want to do. But in doing so, we'll understand, how to configure the pathways, okay, and how to configure the various components just so that we can copy the content at location 0x17 to register B. Actually, let's scratch that. Okay, we'll get to do something like this later. Okay, so the first thing is to copy. Let's see. Copy whatever the program counter is pointing to register B. Okay, that's what we want to do. So the program counter, which is this particular register here, is now being used as a pointer. So if we want to look into this one and convert it into a pseudo C notation, it'll be something like this. Okay, B is representing register B, and it's basically something like this. The asterisk is a C notation for dereferencing. So I'm treating the program counter as an address. I'm dereferencing the program counter, which will get me the content that the program counter is pointing to. Whatever the content is, I want to use it to override register B. So this single equal symbol here is the assignment operator. So this is all we want to do. So now the question is, how do we do this, right? Okay, so we'll start with the first thing, okay, because when you look at this entire operation, you need to start with the program counter. Okay, so the program counter is right here. We see the program counter. So let's make this more interesting. So we'll go to a particular memory location. Let's pick this location here. Okay, that is location 89AB. So this is location B. And we'll change location B to a content of 6F. Okay, you just type it after you click it. So this is this location 0B has a content of 6F. And we'll also change the program counter to 0B. Okay, so there we go. So you can see that it's already selected, and that's because the initial state of the processor is already set up to do something like this. Okay, but we want to find out why. Okay, just because, oh, this is so convenient. Okay, the program counter seems to be specifying the address of RAM already. Well, it seems convenient, but we still want to know why that is the case. So you can start on either side. I personally like to start on the RAM component. Daniel is typing something, but I'm gonna I'll keep talking until I see. Oh, there we go. So when this program is running, program counter is always containing the current address in RAM that is being looked at. I wouldn't call it like that. I would just say that the program counter is one of the things that can tell RAM which address we want to look at. Okay, what location we want to look at. So the program counter is one of the things that can do it. All right. So we'll start with RAM. Okay, so in this case, we'll start with RAM because when we look at what we want to do, okay, when we look at what do we want to do, this is a dereference operation. So any kind of dereference operation means we want to access RAM. So we want to go to RAM and we say, okay, RAM, you need to wake up. In order for RAM to wake up, RAM cell has to be a 1. Okay, so right here, RAM cell is a 1 because it is in light green. The next thing you have to ask is, if we are using RAM, are we reading from RAM or are we writing to RAM? Because those are the two possible operations that you can do with RAM. In this case, let's check out the in this case, let's check out the operation that we want to perform. So the operation that we want to perform has the content of RAM on the right-hand side of an assignment. So that means we are trying to read from RAM. So if we are trying to read from RAM, let me just kind of put this over here. So I can just click on the title bar and make it reappear. Well, or I can just make it appear all the time. So we'll figure that out later. But if we want to read from RAM, then we need to control the LD or the load pin, and it needs to be a 1. So you can see right here, LD, which is the pin that controls whether we are reading or not, is already a 1, and that is controlled by the tunnel called RAM LD or RAM load. Okay, so in other words, we are selecting RAM is paying attention, and we are specifying a read operation because LD is a 1. So the third question you need to ask is now saying, well, okay, this RAM has got 256 locations because the address port has 8 bits. Okay, so because when you have 8 bits, you can specify one of 256 items. So there are 256 locations. The question now is, how do we select this location here, the location that we want? Okay, so now you have to track down the wire going into the A port, going into the address port, and you can see that eventually it basically came from a multiplexer. We talked about what a multiplexer is from last time. It's basically a railroad switch. Okay, in the case of a multiplexer, we have multiple input and only one single output. So the select pin, okay, which is the one that has a little gray dot on top of it, the select pin is the value that let you select one of the inputs. Okay, so the inputs are labeled, the first input is labeled 0, so the second input is input 1. So the value of the selector is the one that specifies which input becomes the output. So in this case, ADDRMUX, which is the name of a tunnel, has a value of 1. So the selector is specifying a value of 1. So that means out of the two inputs, input 0 versus input 1, we want input 1 to connect to the output of this particular multiplexer. So now we say, okay, now let's track down this particular wire. And we can see that wire is coming straight out of the program counter because it's coming out of the Q port of a register. So now all we have done so far is to analyze, and we figure out that this is how we connect the program counter to the A port of RAM, and we want to read. So do we have any questions at this particular point? We might go through this exercise a few times, but every time we go through this particular exercise, it is important to ask questions right away, so that we so that there's nothing undefined and unspecified when we move forward. All right, so I'm going to assume that there are no questions at this point, which is a little bit surprising to me, but that's okay. So the next question now is, I know what is specifying the address. I know that we are reading from RAM. So the next natural question is, well, when RAM outputs the content at the address location, who is paying attention? Because this is a RAM read operation, which means something is reading the content from RAM and trying to probably update itself. So now we have to track down the D port and look at this wire. And we already know that we want register B to be updated by whatever the content is at location 0B. So that content turns out to be 6F. Okay, so if I click on this wire, it will give me a 6F. 0110 is a 6, and then 1111 is an F. You see 111 over here because that turns out to be the unsigned. Let's see. No, this is the signed. Signed interpretation of the bit pattern. This is literally 111. So I just so happen to pick a binary number where the decimal representation also only has ones. Okay, that's completely coincidental. That was not planned, but it just kind of works out that way. All right, so now we want to see, okay, how do I get into the content and use it to update a component or one of the registers inside the register bank? Looking at the overall picture, I cannot possibly answer that question. So what we need to do is look into the RAM, the register bank component. So we right-click on this, we click on View Register Bank. So now we get to see what is inside the register bank. And inside the register bank, we can see this is register B, and register B is the one that needs to be updated. So now we need to ask, in order to update a register, what needs to happen? Okay, now that goes all the way back to the discussion of D flip-flops, okay? Because we talked about edge sensitive and also level sensitive D flip-flop and having both at the same time. So in order to update a register, we need to make sure that it is first enabled. So the EN pin, okay, if I were to magnify a little bit, so the EN pin, which is this particular pin, needs to be a 1 first. Now, how can we make that a 1? Well, it's coming out of what we call a decoder, and a decoder is basically a demultiplexer that has a constant 1 as its input, and that's why it's not shown here. But basically, you can look at it as a constant 1 as an input. So the question is, where do we send that constant 1 to? And that is also controlled by the selection port, which is also the one that has a gray dot on top of it. So we want register in cell in select to be 0, 1 in this case, because this is output 0, this is output 1, this is output 2, and this is output 3. But that's in decimal. So if we want to count in binary, then this is output 0, 0, this is output 0, 1, this is output 1, 0, and this is output 1, 1. And because this 0 output 0, 1 is the one that we want to be a 1, that means the select pin needs to be 0, 1 as well. Okay. Now, this particular decoder, even though it is more or less like a demultiplexer, it also has an extra pin, which is the enable pin. This particular enable pin, if it is a 0, that means the decoder is not driving anything, or all of the outputs would be zeros. So we need this particular pin to be a 1 in order to output a single one out of one of the 4 outputs. So we want this to be a 1. We want this to be a 0, 1. And once we have those set up, then whatever is presented to the D port will update the register when the clock has an uprising edge. And this is the clock line over here. Okay, so this wire connects to the clock, which also hooks up to there's only one single clock of the entire processor. So this clock is shared with basically all of the other clocked components. All right, so knowing all of this stuff here, we want this pin to be a 1. We want this pin to specify 0, 1. And we want this particular pin to connect to the D port, to the data port of RAM. So now we go back to the main, and then we try to look at the equivalence of those particular pins. There are several ways to do this. Okay, so one way to do it is to right-click, go to Register Bank, and then we go to the appearance of the register bank, like so. And now when you click on one particular pin, it will show you in a picture-in-picture format, where is the location of that particular pin. So this is the in cell is the input select. This needs to be a 0, 1. In EN, input enable, is the one that enables the decoder. So that needs to be a 1. And then this in here is the one that connects to the D port of all of the registers. So we want this in to be connected to the wire that comes from the D port of RAM. So when we get back into main, we look at this particular pin here, or this Y here, and say, I want this to connect to this particular wire over here. So now the question is, how do we do that? Well, the only thing that is standing between this particular wire and this particular wire is a multiplexer. In other words, we need to configure this particular multiplexer over here, this one here. Okay, come on, let me select it. So we need to configure this multiplexer so that input 0 becomes the output. Okay, and to do that, we need the select to be a 0. But this one also has an enable too. So a multiplexer can be enabled, or it can be this. There are two types of multiplexers. The one kind has an enable pin, and the other one does not have an enable pin. The ones that have an enable pin allows you to specify whether the output is actually connected to the input or not. Whether you select one or not, you can basically turn off the output. And the ones without an enable pin means it's always on. So this one is not always on. It's only turned on when RIEN is specifying a 1. All right, so now we have specified everything. So let's go ahead and check on our checklist here what is needed. So in order to perform this operation, we need RIMUX to be a 0, 1 in base 2, okay, because we want basically the second register in the register bank to be selected, to be enabled. We need RIEN to be a 1 in order for the decoder inside the register bank to enable, and we also need this multiplexer to be enabled. We need okay, so that connects this particular wire to the data port already. So now we can look into the other side of things. Okay. All right. So from here, when we look at RAM, okay, let me just scroll down a little bit here. So when we look at the RAM component, we need RAM cell to be a 1. We need RAM load to be a 1, because we need RAM cell to be a 1 to basically make sure RAM is paying attention. We need RAM load to be a 1 to specify a read operation. We also need address mux to be a 1, so the input 1 of this multiplexer becomes the actual output, which is then connected to the A port of RAM. So we need ADDR mux to be a 1. And that's about all we need in this case. Okay. And then everything else should be disabled. In other words, the program counter should not auto increment or should not be updated. So its enable should be a 0 and so on and so forth. So this is a fairly simple operation, but we need to specify all of these items here. Okay, RIMux, RIEN, RAM cell, RAM load, and address mux, all of those need to be specified in order to establish the pathway between the RAM, the program counter, and also register B inside the register bank. Do we have any questions up to this point? Because I'm fairly sure that we might have a few questions at this point. So you guys have an opportunity to ask questions. And I am not seeing any questions whatsoever. Okay. Well, in that case, I'm going to continue. All right. Okay, so I'm going to continue this discussion at this point. So now the question is, what is RIMux? Oh, here we go. We got questions now. I think that's part of the reason is because of the lag on YouTube, because YouTube is always at least 10-15 seconds behind. All right, are we supposed to poke the processor to get the wanted values? No. So I will show you how to get this to work. Okay. So the processor is supposed to run a program. So we need to, so instead of poking these wires individually to get the value that we want, there's another way to do it. We are not going to poke it. The only thing we're going to poke is the clock pin. All right, so Tom says, I need more knowledge questions first. So I will wait. Okay. And then Anita is typing something. All right. Can I explain the B equals to star PC part again? Yes. So the program counter, okay, so we got only one memory. The ROM component of this processor is not really exactly considered as part of its quote unquote memory. Okay, so it's a whole separate thing. So when we refer to memory, we are referring to RAM. When we see the notation of asterisk PC, it is a dereference operator, which means we are looking at it's referring to the value at the location that the program counter is pointing to, which is exactly what we're trying to do, because we currently have a pathway between the output of the program counter, which is this wire over here, and the address port. So we have so this particular wire is connecting through the multiplexer to this wire over here, which means the output of the program counter is driving the address port of RAM. And as a result, we are specifying which location in RAM that we want to access. Because the LD pin is a 1, we are specifying a read operation, which means the content at that location is now presented onto the D port. And the D port is going all the way around, okay, to this particular multiplexer. And RIMux, needs to be a 0, 1. We talked about that a little bit earlier. And then RIEN needs to be a 1. Okay, so assuming one is 0, 1 and the other one is a 1, then when we look into, and then RISEL is supposed to be 0, 1. Okay, RIMux by the one should be a 0. So I think I got that wrong. RIMux should be a 0. So I got that part wrong. So I do apologize that I got these two mixed up. So RISEL is the one that needs to be a 0, 1 in base 2. So assuming that really is the case, when we go into the register bank, then we say, okay, this is now a 1, this is now a 0, 1, and this is now connected to the D port of RAM. So with all of these things happening, that means register B is ready to update based on whatever is presented to its D port when we have a rising edge on the clock. And that's how register B got updated to the content that to the content of the location that the program counter is pointing to. And in C and C++, the notation that we typically use to represent that is this. Register B is updated by the content in memory, in RAM, that the program counter is pointing to. So are we okay so far? So these are good questions. These are very good questions. It means you guys are paying attention and trying to comprehend how this thing works. So that's good. So go ahead, keep asking questions. Is it possible to move the notepad lower so we can see what I have typed? You mean like this? Okay. All right, so we got two more people asking. So go ahead. Three more people. Okay, so the question is this update is by reference or by value? I would not use those terms to describe it. We are simply looking at the D port of RAM, and whatever it is, we connect it to the D port of a register eventually and update the register accordingly. So I wouldn't use the terms by reference or by value because it is not inside the context of a subroutine at all. That is correct. Daniel is correct. It is not inside a function, and as a result, there's no context to refer to things as by reference or by value. All right, so the another question is, how can you tell when we need to change in cell input select when we want to reset a multiplexer? Not quite sure what that means. So in cell is input select, which is this pin here. The only job of this particular pin is to say which one of the output would become a 1 as soon as the enable becomes a 1. This is controlling the output. I'll show you what that means, okay? But right now, so this, okay, so this pin here. See, there are 4 here, and there's one implicit input which is always connected to a 1. So this pin, which connects to the select port of the decoder, is deciding which one of the output connects to the imaginary input of 1. That is the job of in-cell or input select. Okay, so I think we still got one question coming, so we'll wait for that. All right, so is it a kind of gatekeeper? Okay, please be more specific. What is it referring to? I think next time I will type in the text channel because it takes way too long for the turnaround between YouTube and Discord. It is not a gatekeeper. All it is a specifier. All it does is to specify which one of the output of the decoder connects to the implicitly connected input of 1. That's all it's going to do. It's a selector. It's not a gatekeeper. All right. So now we have all of these things here, okay? And we can tell that RI mux, RI cell, RIEN, RAM cell, RAM load, and address mux Those are all tunnels. So when we go back to main and we ask, where are those tunnels connected to? So now we track down the tunnels, and we can just point to one, or you can just kind of find all of those. And we can now see where the tunnels are connected to. Here is RIMux, here's RIEN, register input enable. Here's RI cell, which is register input select. Here we have RAM cell, RAM load, and then address mux is down here. Okay, so all of those tunnels eventually connect to basically there are two stages of splitters. So this is one stage of a splitter, this is another stage of a splitter, but eventually everything connects to the D port of ROM. In other words, ROM, the content of ROM somewhere, okay, is dictating how we configure the decoder, the demultiplexer, the multiplexer, various control pins to RAM, and a few other things too. Okay, so all of these things, okay, all of these tunnels eventually are determined by the content of ROM. So ROM is important, very, very important in this whole scheme. Okay, so that means in order to perform the operation that we want to perform, which is the one that we are specifying here in the note, in the little post-it, okay, we need to somehow configure a ROM location to basically have this kind of configuration. And Tom is asking the ROM will never change. That is correct. So you can assume this ROM here is constant. It does not change unless we are quote unquote rebuilding the processor for some reason. But there's no reason to update the ROM unless the architecture itself is changing, or unless we want to implement a new opcode. Okay, so let's not talk about opcode just yet. Okay, but there is a location here in ROM that performs this operation. All right. So do we have any questions about the configuration of multiplexers, demultiplexers, decoders, various control bits to the RAM, just so that we can specify, oh, we are reading a single location of RAM that is pointed to by the program counter, and then we use that, okay, the value at that location in RAM to update register B. Do we have any questions about the pathway of all of those things? Yes. So the ROM needs one location for every combination of zeros and ones that we need to control all the multiplexers, demultiplexers, RAM, and other components. Yep. All right. So here's the deal. Okay. So the deal. Okay. If you want to use an analogy. Okay. So the ROM is really important. You can kind of think of the ROM as the music score of a complicated piece of music. So think of those famous pieces by Beethoven. Okay, it's a very complex piece of music. It involves many different instruments and whatnot. Okay, this portion of the processor is the conductor. Okay, this is the conductor reading the score with all of these different parts. And then these other components over here, including the ALU, the register bank, the RAM component over here, the program counter down here, the instruction register down here, and so on. Those are individual or groups of instruments in an orchestra. So yeah, I knew somebody would like it, but there's another analogy too. But so I'll finish this one and then we'll talk about the other analogy. So now, what about the clock? Right? This is the clock. The clock is the metronome. The clock is the one single metronome that provides the time base for the entire orchestra. So everybody can hear that metronome going tick tock, tick tock, tick tock. Okay. But the conductor is the one that will read from the score, and then it will tell the violin to hush, the flutes to play in a loud way, and also the cello to kind of soften up a little bit, and so on. So the conductor is actually controlling everything, but by doing so, the conductor needs to read the score. The score is the one thing in ROM. Okay, so that seems pretty easy to understand. But what dictates which location in ROM that the conductor needs to read? That turns out to be in RAM. Okay, remember the contribution of John von Neumann, right? His contribution is to say, well, instead of hardwiring everything, like this instruction is after this instruction, after this instruction, and they're all done by wiring, physical wiring, let's store instructions in RAM. So we are actually storing instructions in RAM. Okay, so there's this part of the discussion. So we'll go off and do something that seemingly is not connected to what we just talked about, okay? But there will be a connection at some point. So I'm going to go to the shared drive, okay? So we go to the shared drive. You can do the same if you want to, on your own, because it is visible to you as well. So let me just kind of navigate to the shared drive and to the processor subfolder. So inside the processor subfolder, we got a lot of tools, but one of them is not a tool, it is a table. Okay, all it wants to do is to explain certain things. So now we want to look at the opcode table, and here it is. So when you look at the opcode table, you will see, like pseudo C notation in column C to explain what a particular mnemonic is going to do. In column A, we see a bit pattern that specifies all the zeros and ones that needs to be specified in RAM so that we can specify what operation we want to perform. So when you look through all of these things, you will see one that seems to be familiar. So we'll pick the one that we just looked at, which is LDI. So let me see, where's LDI? Should be one of the one at the beginning, right here. So we look at this and go like, well, that looks vaguely familiar, because instead of register B, I use a placeholder called X over here. So X is a placeholder, and if you read the key to this particular table, X and Y, each one can be one of the 4 registers. So X is simply a placeholder for A, B, C, or D. And then when you look at the right-hand side of the assignment, it looks similar to what we want to specify, which is dereferencing PC. But this one also has an increment of the program counter, okay, which seems kind of odd. Okay, why would we want to auto increment the program counter? Okay, so we'll get to explain all of that stuff in just a little bit. Okay. So this is the bit pattern that you need to specify in RAM. And you need to substitute XX, which specifies 2 bits, so that those 2 bits in return will specify register B. And the key right at the beginning here says XX specifies one of the 4 registers. If you want to specify register A, XX needs to be 00. If you want to specify register B, which is what we want to do now, XX needs to be 01. Oh, okay. So that means if we want to specify that register B should be updated by whatever the program counter is pointing to, then we want this XX to be 01. So that will make the instruction 6, because 0110 is a 6, 1101 is a D. So 6D is the opcode that we want to specify. So column A specifies the opcode pattern. Now, if you say, oh, I can totally write the entire program using just opcodes because I have a superhuman capability of remembering bit patterns and stuff like that, then you do not need column B. You do not need an assembler, because now you can just write the entire program using a whole bunch of zeros and ones like this. Okay? Is it possible? Yes. Do I want to do it this way? No. Okay, because I want free time to do other things that I actually enjoy doing. Okay, and this is not one of the things that I enjoy doing. Okay, using all my brain juice, just to put all the zeros and ones together. So that is why we want to use, what column B is referred to as the mnemonics. Okay, so a mnemonic is basically um, a slightly more user-friendly way to represent an operation. Okay, that's the best way I can explain what a mnemonic is. So LDI stands for load immediate. It requires two things. X is specifying a register, and then I specifies the value that you want to store into register whatever X is representing. Okay, so that looks kind of odd. It's like, that doesn't seem to make sense. Okay, so we'll basically find out why it does make sense at some point. Okay, so I can only be a constant. Okay, I is not the location of RAM. It is just a constant. All right, so are we doing okay so far with explaining the explanation of what is a bit pattern, which we refer to as the opcode, and the equivalent representation that is slightly more readable that we call the mnemonic. So is that okay? Does everybody understand the difference between these two? This is what the processor natively understands. This is what we prefer as humans. So the assembler is the translator translating mnemonics into the binary opcode. Eden's typing something, so I'm gonna wait a little bit here. All right, so the first 4 bits are called no, it's not the first 4 bits. It's the entire 8 bits. It's called a single opcode. So right here we are defining a family of 4 individual opcodes, because 6C, 6D, 6E, and 6F, those are all opcodes that belong to the same family of LDI with a particular register. Okay, and here we have 3 questions coming. All right, exciting. All right, so the first question is why we have XX at the end of the opcode, because XX specifies one of the 4 registers. So instead of using 4 different rows and have only one row to say this is how we specify loading something into register A, this is how we load something into register B, and this is how we load something into register C, and this is how we load something into register D, I just say nah, let's just use XX, for the bits that need to change depending on which register we are loading into. So that is why we have XX, and XX does correspond to X. If X is A, then XX is 0, 0. If X is B, then XX is 0, 1, and so on. Oh, I think I just answered that question, Christy. So that's a very good question, because it is just a little bit ahead of what I was about to explain. So that is good timing. But does that answer the question though? Did I sufficiently answer the question of how to specify which register we want? If we say LDI A, then XX is 0, 0. If I say LDI B, then XX is 0, 1, and so on. Okay, excellent. Cool. All right, so I think we are ready to actually use the assembler to assemble one mnemonic, look at the binary representation, and then run that one single opcode in the processor. Okay, so we're going to spend the next probably 15 minutes to do it. Okay, but this is super important. Okay, so you might want to just kind of jot down the note of what the current time is, because you might want to refer to this time in the video. Okay, in the future. Okay, so I think this is going to be important. So now we go back to the folder, and then we use the assembler. Remember, the assembler is really just a translator to translate from mnemonic into opcode. So we go to the source tab, and because this is a single instruction, we can just go ahead and type it in. Okay, so we'll just type in in a particular cell, type in LDI, which is the opcode. We want register B, and the immediate value can only be specified in base 10 at this point. So we're going to have to specify in base 10. Let's try 111, which is 6F, right? Okay, so we'll give it a try like that. Press the enter key. The assembler is going to take some time, okay, and okay, it didn't take a whole lot of time because this is a really short program. So this is already done. So when this is done, the first thing is to answer question number 4 in the lab. Okay, so we go to the assemble tab first. So with the assemble tab, okay, I kind of hit all the other columns because those are not really important for the most part. So I only expose column V, W, X, and Y, and you can see that each one is commented. Column W is the address in hexadecimal. Column X is the opcode in hexadecimal, and column Y is the immediate constant in hexadecimal. So you can see that this is corresponding to address 0. But every byte has an address, and yet we have 2 bytes being specified here. Column X is 1 byte, column Y is another byte. So now the question is, which one has the address of 00? I shouldn't say we, but in this part of the world, most people read from left to right. So that means column X, the cell of column X, specifies the content that column W is specifying. So that means 6D in this case is the content of location 00. So what do you think 6F is corresponding to? The next byte, right? Okay, I'll let Tom type out what he's about to type out. All right, so Tom is saying exactly. So the next byte. So if 6D is at location 00, what is the location of 6F? 6F is the content of which location? Tom is correct that it is the next location. So what is the location next to location 00? That will be location 01. Okay, so that's why if we do have a second line over here, it will be at location 2 because location 0 is has a content of 6D. Location 1 has a content of 6F. Then location 2 is going to correspond to the next instruction. All right. Now, when we look at the RAM file, okay, it is actually clear that the content of this RAM has 6D and 6F. So we're going to go ahead and download this. Okay, so we download it as a CSV. And I usually put it into the temp folder. If you're using Windows, okay, you might want to have a particular place to put your CSV file. So I'll just call this LDI, okay, because it is for testing the LDI instruction. And then we save it. There we go. And then we switch back to Logisim. So if you are in Logisim and you say, I want to start running a new program, okay, it is usually safe to reset the simulator first. So you go to the simulate menu and then you click, reset simulation, or you can type Control-R to reset the entire thing, okay? So you reset it, but keep in mind that resetting simulation also reset the content of RAM. ROM is fine, okay, but RAM is completely cleared when you say reset the simulator. So now we have to right click on the RAM component. We say load image, and then we specify the location of the CSV file, which is in the temp folder. It is called ldi.csv. Press the enter key, and now we can see that 6D is at location 00 and 6F is at location 01. Okay, that's the easy part. the difficult part now starts. Okay, so this is the part where you might need to listen to this part again, like a few times. So don't worry if you don't catch everything the first time. Okay, you might need to listen to this several times to make connections between all of the concepts. But where we start is important, because where we start is microcode pointer. Microcode pointer is a register, but you can see that it has 3 digits instead of 2. Okay, that's because the width of this particular register is different from the other registers. But 000 is 000. Okay, and you can see the output of this register is connected to the address port of the ROM. Okay, which means 000 is the location that we want to look at. And by the way, this ROM is always selected because the select pin, is connected to a constant of 1, so it's always selected. We don't need to turn it off ever in this particular processor. So the content that is at location 000 is this kind of rather long hexadecimal number, 1080007. Okay, now if you really feel like it, okay, you can translate this hexadecimal number into a long binary number and then figure out which bit is which bit. Okay, but that's kind of a hassle. So that's why I have all of these tunnels set up, and the tunnels have a name. So this way it is easier for myself to figure out which one is which one. So we'll track down all these bits here. The ones are the wires that are ones are particularly important. So we look at this particular wire and say, hey, that's a 1 over here. It is corresponding to bit 0. What is it doing? Okay, so we look at this and we can see that it is enabling the instruction register, which means the instruction register is going to update in the next rising edge. Okay, because that is how most of the registers are set up, is they update on the rising edge of the clock line. Okay, so this is basically saying, okay, let's prepare the instruction register to be updated. And as soon as you see that a register is about to be updated, what do you think is a natural question to ask? Without even looking at all of the other bits, okay, what is the natural question to ask if a register is about to be updated? I would say, who is specifying the new content, right? Because if you're updating something, okay, what are you updating it to? So now we want to track down what is connected to the D port of this instruction register. Okay, so we track down, and Logic makes it easier because you can click on the wire and it will basically highlight everything that is connected to that wire. And you can see it goes to many different places. Okay, so now you have to say, do you think this demultiplexer is going to specify the content on this wire? The answer is no, because register output 0EN, or the enable pin of this demultiplexer, is a 0. So that means this particular demultiplexer is not going to output anything at all. So it does not contribute to the wire that is currently being selected. All right, if that is not doing anything, let's check out the other thing that connects to this particular wire. It is the D port from RAM. Okay, so when it is going to the D port of RAM, then you have to ask, well, is RAM even awake? Okay, are we even telling RAM to do anything? Well, the select pin says yes. Okay, so RAM cell is a 1, which means yes, we are telling RAM to do something. So whenever RAM is about to do something, then the next question to ask is it reading or is it writing? Okay, and that's determined by the load pin. The load pin is a 1, which means we are reading from RAM. Okay, so that answers the original question of what is specifying the new content of the instruction register. It is RAM. Okay, the content of RAM presented at the D port is now going to update the instruction register on the next rising edge. Okay, when the clock goes from 0 to 1, then we are taking whatever is the output of RAM, at the D port, to update the instruction register. Good. Okay, we have just asked a few questions and answered those few questions. But then we got new questions, okay? Because whenever RAM is involved, okay, knowing that we are reading and where the D port is going to is great. But we got another question. The other question is, who is telling us where we are supposed to read? Okay, so that's the next question to ask. That question can be answered by tracking down whatever is connected to the A port or the address port. Okay, and Aiden is typing something, and I'm gonna pause a little bit. Light green is a 1, dark green is a 0. Black wires are they are not single bit wires, and that's why they cannot use a color to indicate its content. So a black wire is a multi-bit wire, and as a result, it cannot reflect the content just by using light versus dark green. So you actually have to poke the wire to find out what is the content on that wire. So that's a good question. Okay, very good. Okay, so getting back to our question, okay, who is specifying the address port? So we track this wire all the way back to the multiplexer over here. It's a multiplexer, which means it has multiple input and one single output. And the select pin is the one that is under the gray dot, right? So the pin under the gray dot has a wire that is light green connected to it. That means a 1. Okay, if you click on it, it will say a 1 as well. Okay, so this one is basically saying input 1 is connected to the output of this multiplexer. And because it doesn't have an enable pin, it means it is always enabled. So we don't have to worry about this multiplexer not being enabled. It's always enabled. Yes, for the most part, Tom. 1 is usually meaning on in this design. But this one does not mean it's on. This one means we are using input 1 to connect to the output. So it's very important to understand the gray dot, the significance of the gray dot. The gray dot is basically saying this is the selector, okay? Which input should connect to the output? Or if you have a demultiplexer, then it determines which output is connected to the input, okay? So the direction is opposite, but nonetheless, whatever is under the gray dot is called a selection. So because the selection says input 1, so now we track down input 1. Input 1 comes from the program counter. So now we know the program counter, which is initialized to 00, because when we reset the simulator, all registers are reset to 00. So the program counter is 00 because we just quote unquote power up the processor, and that is telling the processor to access location 00. Whatever the content is, in this case 6D, is being read, and it's going to update register, the instruction register, which is here. Okay. So now that we have established all the pathways that we actually care about this operation, it's time to do a control T, which makes the clock line go from a 0 to a 1. So control T right here, and we can see after the control T, the instruction register is now updated to the value that the RAM component is outputting, which is 6D, which is also known as 111 109, sorry, in this case, in base 10. Okay, so that completes what we call the fetch cycle. So this is also something that you might want to write down. Okay, so the fetch cycle is going to read. The fetch cycle basically is saying the instruction register, INSTRREG, is getting whatever the program counter is pointing to. That's called the fetch cycle. Then the next question is, now that we have read whatever the content the program counter is pointing to into the instruction register, do we still need the program counter to be pointing there, at this point? The answer is no. Okay, so that means we at some point we want to increment the program counter, but not right now. Okay, So right now we are about to experience a falling edge of the clock line because the clock is high at this point. So the next transition of the clock is going to make it low again. Okay, Christy has a question, so let me wait for that. What does Control T do? Control T toggles the clock line. So if the clock line is a high, Control T makes it low. If the clock line is a low, then Control T makes it high. It basically just inverts the state of the clock line. All right, okay. So which is a very important tool because we want to single clock, okay, or single edge, I should say, the simulator when we are at the beginning of this discussion, okay? Later on, we can probably do it at a faster speed, but right now, we need to single clock. So if I type Control T again, this clock is going to go from 1 to 0 because it's a toggle. But now it is important because we need to click on the microcode pointer. All of the other registers would update on the rising edge, but the microcode pointer is the only one that would update on a falling edge. So we are about to update the microcode pointer. If I type Control T again, it will update the microcode pointer. Why? Because the microcode pointer is always enabled. Okay, and we know that because when we track down the enable pin of the microcode pointer, we can see that it is always connected to a 1, the constant. So we know the microcode pointer is always enabled so it will always update on the falling edge. Okay, so what do you think is the next natural question now that we know the microcode pointer is about to be updated? I think we encountered this earlier, right? Whenever a register is about to be updated, the natural question to ask is, who is supplying the new value? Okay? To what? Exactly, Daniel. I think Aiden's about to type something to the same or similar effect. We should make this kind of like a Jeopardy game, right? You guys have to hit that buzzer as quickly as possible. All right, so yes. So now we look at this Y and go like, okay, unfortunately this Y is coming from a multiplexer. But that's okay. We know what a multiplexer is going to do. A multiplexer has 2 inputs or more, and then the select pin will tell us which input connects to the output. Cool. The select pin sets 1, so that means we need to track down input 1 to the multiplexer, which is this Y over here. This wire is coming out of an adder, okay? This is an adder, can you guess what an adder would do? All it does is to add, right? So the question is, what is it adding? These are the 2 inputs, okay, to specify what is adding. Then go like, well, if we add 0 to whatever the microcode pointer is, then we just get the exact same value back as the output of the adder. There would be no point in doing this. Well, but it does have a C-in or the carry in, okay? Carry in is the same thing as K0 in our discussion of the binary addition thing. So this one is part of what we're adding. In other words, if you want to know what we're actually adding to the microcode pointer, it would be the sum between C-in and the other input, okay? And this is a 1, that's a 0. 1 plus 0 is a 1. So if we are actually adding 1 to the microcode pointer at this point. So when you look at the actual content coming out of the adder, it is actually a 1. And this 1 eventually will go through the multiplexer, going back into the D port of the microcode pointer. So that means, wow, this is a long way to explain increment. Okay, we are simply incrementing the microcode pointer on the falling edge for in this particular instance. So if I type Control T on the keyboard, we would expect the microcode pointer to become, guess what? 0, 0, 1. Woohoo! Exactly like what Daniel said earlier. Epic. Okay. Now, because the microcode pointer is connected to the A port of the ROM, now we are selecting or addressing location 001 in ROM. which has a slightly different bit pattern over here. So we look at this particular bit pattern and go like, oh, okay, this time what is it going to do? So the most important wires to track down are the ones in light green, because light green means a 1, and it usually means we're enabling something, or we are doing something that is important. Okay, so in this case, we can see the PCEN is in light green, so we might want to track this one down. Okay, and once again, in LogicSim, it's easy to track down something because you can click on a particular wire. If it connects to a tunnel, then everything connected to that tunnel will be highlighted as well. So now we can track down. Aiden is typing the rightmost 4 means RAM load. The rightmost 4 means RAM load. I'm not sure. RAM load is right here. I'm not sure about the rightmost 4, like in ROM. Oh, you mean this one here? Yes, because that's okay. If you have 4, 5, 6, 7, and then C, D, E, or F, that means bit 2 is a 1. Because because RAM load is bit 2, and we don't know what it's going to read like as a hexadecimal digit if we just know one of the bits being a 1. So a whole bunch of hexadecimal digits can correspond to having bit 2 being a 1. So we have to be careful. But Aiden is correct that in this case, this 4 is telling us that RAM load is a 1. Okay, so that's good. But RAM sub is a 0, so that means RAM is not being used. So that means RAM load is insignificant at this point. So we want to track this one down first, okay? Because PCEN means the program counter is enabled. So we track it down, and sure enough, PCEN is the wire that connects into the EN or the enable of the program counter. So once again, we ask that question, right? It should be getting boring at this point, okay? When the register is about to be updated, what do we ask naturally? What are we using to update the register, right? So that is the question that we want to answer at this point. So now we track down the wire connected to the D port of the program counter, and we go like, okay, it's coming from a multiplexer again. Well, that's how we can we can switch the railroad, okay, so that the train can go to different places, okay. So in this case, PC mux, for whatever reason, okay, is a 0. Okay, I know exactly for what reason, but as far as we need to know, it is a 0. So that means input 0 is the one that we are using in order to update the program counter. It's coming from an adder. You go like, oh, tech, I think we have just seen this before. We are just adding 1 to the program counter, and so the program counter is incrementing. You're absolutely right. That's exactly what we're doing with the program counter. Okay, so now if we go back to the explanation, posted over here, we can now say, oh, okay, the next thing we want to do is to increment the program counter. So because the incrementing of the program counter happens after the dereference, if you want a very obscure way to write this, it is the same thing as star PC++, but you want the plus plus to be inside the parentheses. Because what we're incrementing is not what the program counter is pointing to. We're incrementing the pointer at the program counter itself, but we want to do it after the dereference operation. So the fetch operation, actually includes both dereferencing the program counter to grab that byte into the instruction register, but the auto increment right after, well, that really is a part of the fetch cycle, because after we read that byte into the instruction register, we don't really need that byte anymore. We don't need to point to that byte anymore, so we should point to the next one. Okay, so that's the fetch cycle. Now it is time for falling edge, right? So falling edge means only one particular register will update, and that's the microcode pointer, because all of the other registers, including also RAM, would only update on the rising edge. So, oh, okay, I haven't do the rising edge first. So let's do a Control T at this point. So when we do Control T, observe the program counter. So Control T right here, and you can see the program counter just increments. Cool. And then what, right? So now that the clock is high, we want to see if I Control T again, clock is going to go low again. So we now have a falling edge. The falling edge only affects one thing of the entire processor. The falling edge only updates the program, the microcode pointer. So we are expecting the microcode pointer to update. Then you might say, oh, we know what it's going to do. Well, do we? No, we don't, okay? Because the whole reason why we have select pin is sometimes we want it to auto increment, but other times we do not, okay? So we track down the D port. It's coming in from a multiplexer, okay? We have seen this before. But this time, the select pin of the multiplexer is a dark green, which means we are now selecting input 0 to connect to the output of this particular multiplexer. Then we look at this and go like, that is kind of interesting, because a part of this wire, through the splitter is coming from the instruction register, because if you highlight this wire, you can see, the other half of the splitter is highlighted as well. But the other part is connected to just a constant of 0. What are we doing here? Well, we are really just padding 4 zeros as the least significant bits, and then the most significant bits are really just coming from the instruction register. So let's take a closer look, because I think some of you are asking, what are we talking about here? Okay, so let's take a closer look at what the little numbers here in the splitter. You can see that bit 0 to bit 3 are coming from the constant of 0. So that means bit 0 to bit 3 going into this multiplexer are guaranteed to be 0, 0, 0, 0 in base 2. Okay, that's just a constant. What about bit 4 to bit 11? There are 8 bits in bit 4 to bit 11. Those are all coming from the tunnel that we know as instruction. So the tunnel instruction is actually really just the output of the instruction register. The instruction register has a content of 6D in hexadecimal at this point. So that means to the input of the microcode pointer is going to be 6D0. Okay, so if I click on this wire, it would just say it is 6D0, or the binary representation of that. We can see a 6 being 0, 1, 1, 0. D is 1, 1, 0, 1, and then 0, 0, 0, 0 over here. So are we getting this okay? Do we understand why the microcode pointer is about to be updated to 6D0? The 6D is coming from the instruction register. The 0 in hexadecimal is padded in artificially. We are just introducing those 4 zeros as the least significant bits. All right, we have 2 questions coming in. As they say, we got incoming. What is giving you the value of 1744? That's the signed interpretation of these bits. So 1744 is the base 10 signed interpretation of these 12 bits. All right, where does instruction register get its value? We just did it. The fetch cycle is how we got the 6D into the instruction register. So you might want to roll your time back to I think it's 746. That's the time when we started to talk about the fetch cycle. That's how we got the 6D into the instruction register. So that means, oh wait, hold on a second here. So that was a very good question, because Darwood's question is now saying, okay, so we are using the content of a RAM location that the program counter is pointing to eventually control where we need to go to look at in ROM. And you will be correct about that, okay? That is completely correct. Okay. So now we are ready to have a falling edge, which means the microcode pointer is about to update to 6D0, which also means in the ROM we'll be looking at the content of 6D0. So before we go there, okay, I'm going to write down here, after the fetch cycle, we now have a decode cycle. So the decode cycle, if you want to use the notation that we have at this point, is the microcode pointer getting whatever the instruction register has, but we'll left shift it by 4 bits. That's the decode cycle. Okay, it just takes whatever the instruction register has, which came from RAM earlier, and then we shift that bit pattern by 4 to the left hand side so that we end up with 4 zeros as the least significant bits. That's all we're doing. Okay, that's the decode cycle. The reason why we're shifting is because I want to allow many locations for one single instruction. So I want to allow multiple locations in ROM corresponding to one single opcode. So I just over prepared. Okay, I allowed 16 locations in ROM corresponding to one single opcode, and as it turns out, I really only need 2 for most of them, for all of them actually. So I over planned. Yes, planning ahead, which is not something that I'm known for, but in this case, I did. Actually, I overdid it quite a bit. All right, so let's do a Control T, and we'll see that the microcode pointer will become 6. What was it again? 6D0. Okay, so Control T. Here we come. All right. Nothing too surprising because we have been expecting this, right? 6D0. So the location at location 6D0 in ROM, we see this kind of, we are seeing another bit pattern coming out of it. Okay, so we want to look at, okay, what is going on? Okay, we see the program counter is enabled, so that means we need to track down how the program counter is going to be updated. We can see that RAM cell is a 1, which means RAM is in use in this particular cycle. We see that RAM load is a 1, which means we're reading from RAM. We see that, hey, we see that RIEN is a 1. Okay, register input enable is a 1. So some register is going to be updated, in this particular cycle. So we might want to click on RI cell or register input select and see who is getting updated. Oh, it's a 0, 1, which means register B is going to be updated. That sounds oddly familiar, right? So let's kind of check out what is happening here. So first of all, we go to RAM because RAM cell is a 1, so we naturally just go to RAM and say, okay, what is going on here? RAM cell is a 1, RAM is being used, RAM load is a 1, which means we are reading from RAM. So now the question is, who is driving the address port? So we track down the address port, right? So it goes from, it's coming from the multiplexer. The selector of the multiplexer has a 1, which means it's coming from input 1. And input 1 is coming from the program counter. Hey, that looks oddly familiar. We're using the program counter to specify the address port. So the next question is to say, okay, we know we are reading from RAM. Okay, who is getting updated by the content that we are looking at right now? Okay, so we now need to track down the D port. Okay, the D port goes to many places. So it does go to the instruction register, but guess what? The instruction register does not have the enable pin being a 1. So even though the data is presented to the D port to the instruction register, nothing is going to happen because it is not enabled. So enable is for this purpose. Okay, the whole purpose of the enable pin is so that we can select who is getting updated when a wire is connected to a lot of different components. Oh, it's connected to this demultiplexer too. It's okay, don't worry about it, because register output 0 enable is a dark green, which means this particular demultiplexer is not even waking up, it's not doing a single thing, it's not outputting anything at all. Okay, all right, where else does it go? It goes to this multiplexer. Okay, so we look at this multiplexer and say, Well, this multiplexer has an enable. If the multiplexer is not even enabled, we don't have to worry about it at all. But it is, okay, because this wire connects to the enable of the multiplexer. So the multiplexer is driving the output. So now we have to look at the selector. The selector is RI mux, okay? It is a 0. So that means we are indeed connecting input 0 to the output of this multiplexer. So input 0 is coming from the data port of RAM. So that means we are indeed connecting the data port of RAM into the register bank, okay? So now we need to look at, okay, which register is selected as the input register. We click on this Y. We clicked on it earlier before. RI cell is a 01. Now, if you don't believe me, it's okay. You can go in, right click, and then click View Register Bank. So now that we're inside the register bank, we get to see more details. This is the enable. This is RIEN. So RIEN is enabling the decoder, which means, okay, decoder, one of the output needs to be a 1 now, okay? So the next question is, which output should be a 1? That is determined by the selector. So the gray dot here is the selector. The selector is 0, 1. So that means, output 1 of this decoder is a 1. And that happens to go into, guess what? Register B. So register B is enabled, which means it is about to be updated. The data port of register B, just like the data port of all of the other registers, they all connect to register in, which is really just the register input, to specify the content. No roll call today. It's okay. Yep. So let me just type here so that people can see that. No roll today. Oh yeah, there. Let me see. Let me finish this explanation first, and then we'll see whether it is okay to release the lab or not. Okay, because the lab does refer to what we are talking about, but it also refers to something else. So I'm going to take a quick look after this. Okay, so we'll finish this discussion first, and then we'll take a look at the lab and see whether it is okay to release it tonight or not. Okay, so we track this down and go like, oh, okay. So we can see how in the next rising edge, if I type Control T again, the clock, which is here, is going to go from 0 to 1. And as a result, whatever is presented here, which is 6F, is going into the D port. And because register B of the 4 registers is the only one that is enabled, so register B is going to be updated. Okay. All right, so let's go back out to the main, because we can actually observe register B from here as well. Okay, so this is also just mirroring whatever register B has inside the register bank. And zooming out just one more level is important, because we would see that the program counter is updating as well. So you can see how the program counter also has its enable being a 1. So now the question is, how is the program counter going to be updated? So remember this, every time a register is enabled, we want to ask the question, how is it getting updated? So we track down the input into the program counter. It's coming from a multiplexer. And the multiplexer says, let's go for input 0, okay? And input 0 is coming from the adder. So we are auto incrementing the program counter. The program counter will first be used to specify what location we want to read from. Then it's going to update to 02. Okay. So what we can now expect is the 6F here is going into register B. And then right after that, the program counter will then update to a 02. Okay. Now, in truth, they're actually happening at quote unquote the same time, but because of latency, okay, we don't have a problem of getting the rug to pull under ourselves. Because right now at this point, register B is already seeing 6F as its input. All that is missing is a rising edge at the clock. The program counter has to go through a bunch of stuff and go to RAM in order to update the location. The RAM is the location that is being selected in RAM. That is a super lengthy process, and that's why it is not a problem to do something like this. Okay, so let's observe what's going to happen. Okay, I'm going to scroll up so that we can see register B, and we can also see the program counter at this point. Okay, so Control T is right now. Control T. There we go. So we can see register B is now at has a new content of 6F. Okay, just as expected. The program counter is now updated to 02. And if you look at RAM, okay, we are now pointing to the next location. Okay, and now the question is why are we doing this? Remember, the program counter in the fetch cycle is used to read the next opcode, right? 6F is not an opcode. 6F is the data that we want to store into register B, but 6F is not an opcode. So if I had a new opcode, if I had another instruction after the LDI instruction, it would have been here. It would have been at location 02 in RAM. Okay, so this is all good. We're about to be done with executing one single instruction. Okay, all of this work just to execute one instruction. We're almost there. Okay, so now that the clock is high, the next transition means it's going to go low again. So when the clock goes from high to low, we only have to look at one single register, which is the microcode pointer, this guy over here. So we know that it's going to be updated when I type Control T again. So we want to know how is it going to be updated. We track down the input. It comes from a multiplexer. The selector of the multiplexer says input 1. So we track down input 1, and input 1 is just going to increment. In other words, we are expecting to see the microcode pointer to become 6D1, right? Okay. So when I said, we expected to do blah, 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 it means that's not what you're going to see. Okay, so you guys are going to think, so if we are not going to see 6D1, what are we going to see? Control T comes right now. Control T. You go like, whoa, wait, hold on a second here. Why is it getting back to location 0, 0, 0? Okay, so if this is the puzzle that I'm giving you and your life depends on it, how would you solve the puzzle? Given that you have the simulator, you have the content of ROM, and so on and so forth, what would be the first thing that you check? Magic. Well, very nice, Ethan. Very nice. I did mention if your life depended on this, right? What would you check? Okay, if I want to know why are we now at location 0, 0, 0 again? What is the one part that does not make sense to you? The microcode pointer is supposed to be at 6D1, right? But now it's back to location 0, 0, 0. So maybe, just maybe, it has something to do with 6D1 or whatever content is at location 6D1. There's also another way to look at this, okay? The other question is, what can possibly change the content of a register? And you guys all know this already because I have mentioned this many, many times in today's lecture, okay? The enable has to be a 1, okay, checked. And then we have to have a falling edge, checked, okay? And when we do have the falling edge, the data pin is going to update the register. And that is also checked. The data pin is 6D1, was 6D1 when we had that falling edge. But yet, the microcode pointer is reset to 0, 0, 0. So now you have to think, what is the other way to update a register? A register can also be reset to 0 because it has this little pin here that has a 0 on top of it. That is our reset, okay? So that means, okay, so that means a possible explanation is that the microcode pointer got reset to 0, 0, 0. So now the question is, what can possibly cause that to happen? Okay, so this wire would have to become 1 for a very brief amount of time. but this Y is coming from a OR gate, right? So, in order for the output of OR gate to become a 1, at least one of the two inputs had to become a 1. This particular one connects to a button, okay? It's actually quote unquote a button that you can click on, and you click on that button, it would make it a 1. I didn't click on a button, okay? So it is not coming from the reset tunnel. So it has to be coming from the other one. So the other one is coming out of ROM, out of bit 25. Bit 25 is the most significant bit of the output from the ROM. So whatever happened must have set bit 25 in order for the microcode pointer to be reset to 0. But we know that bit 25 was not a 0 earlier, okay? Because the whole thing is being recorded, right? We can always roll back in time and say, no, bit 25 was not a 1. We have never observed bit 25 being a 1. So now the question is, all right, so what can possibly cause bit 25 to become a 1? And it only has to be for a very short amount of time, because the microcode pointer is instantaneously reset to 0. As soon as the reset pin is a 1. So we have to think about location 6D1, okay? Because we did get to that location. It's just that we did not stay at that location, okay? So now we right click on the ROM component. We go to edit content. Okay, let me resize this window so it fits within the recorded area. Okay, maybe too much. All right, so we go to location 6D0 first. Okay, so we scroll down to 6D0, which is this one over here. That is something that we have seen already. Okay, so don't worry about the bit pattern over here. The next one is the one that we kind of have to think about. Okay, it's 2 followed by 1, 2, 3, 4, 5, 6 zeros. So the first question is, how many bits is a 1 in this hexadecimal number? 2 followed by 6 zeros. Well, we know the 6 zeros are all zeros, right? Because one hexadecimal 0 is equivalent to 4 binary zeros. So we basically know that there are 24 zeros in binary in this particular number. Okay, what about the 2 itself? 2 itself is 1 0 in binary, right? So since we know bit 0 to bit 23 are all zeros because of the zeros in hexadecimal, and bit 24 is a 0 because it is the 0 of 1 0, so that means bit 25 is the 2. This 2 here is bit 25 alone being a 1. Okay, remind me again what is so important about bit 25. Close this. We look at bit 25 and go like, oh, so bit 25 is the one that goes into the OR gate. So if when bit 25 becomes a 1, the output of the OR gate would also become a 1, then the microcode pointer is reset to 0 instantaneously. That was how we cleared the microcode pointer. Then, okay, so now what do we do? What are we about to do now? Guess what? We are about to start the next fetch cycle. We are now going to whatever the program counter is pointing to in RAM, grab that byte, put it into the instruction register, and then we put that into the microcode pointer, and so on and so forth. Okay, and you might think, okay, I think that's the end of today's lecture. No, not yet. Okay, there's a little bit more. Just like the infomercial. But wait, there's more. Because there really is more. Okay, so now you go like, but Tech, you only specified one instruction in the assembler. Okay, there's nothing else to execute. Oh, I beg to differ. Look at the RAM content here. We got the opcode of 0, 0. That is an opcode. I mean, at least the processor will try to look at it as an opcode, right? So now the question is, man, what is it going to do? Well, this is going to be an easier one. Okay, so I'm going to explain this one in a quicker way. So we are going to kind of fast forward just a little bit, okay? And Aiden is correct. This is the no op instruction, but we want to know how it works, right? Why is it called the no op instruction? So you can probably kind of imagine what's going to happen, right? So the next rising edge is going to put that 00 into the instruction register. Okay, so here is the control T that we need. Aha, okay, instruction register becomes 00. Then we have the falling edge. The falling edge is going to increment the microcode pointer from 000 to 001. Not a problem. Here we go. And then we have another rising edge, which is going to auto increment the program counter, because now we have read the content at location 02. The program counter can now advance to the next location. We got that. Control T, the program counter is now pointed to 03. And now we're going to have a falling edge. And we know this falling edge is going to be tricky because all it's going to do is to copy whatever the instruction register has to become the most important, the most significant part of the microcode pointer, and then pad 4 zeros, or pad 1 single zero in hexadecimal to be the least significant digit. Wait, hold on a second here. Are you telling me, I'm pretending to be you, are you telling me that the instruction register, which is now 00, is going to specify in the end 000 to the microcode pointer? Because the most significant 8 bits of the microcode pointer will be coming from the instruction register, and then the least significant 4 bits is just basically a constant of 0 in hexadecimal. So that means when we update the microcode pointer again, which is on the next control T, it's going to reset to 000. You would be absolutely correct if that was your prediction. Okay, so we now say control T. Aha, it's going back to location 000. So this time it's not because of the reset pin being a 1. This time it really is because we had an opcode of 00. So what is going to happen now? The program counter is pointing to location 03. So we're going to read whatever is at location 03 in RAM as the next opcode. And guess what we're going to have? Another 00. Okay, so the opcode of 00 is corresponding to the mnemonic of no op. Okay, so let me go back to the spreadsheet here. So if you look up, I think it's one of the first item. There we go. So when you look up here, okay, we have all zeros as the opcode. The mnemonic is no op. Okay, don't ask me why it is NOP. Okay, why is it abbreviated to just NOP? But that's kind of the convention. Okay, it's no op or NOP, right? So no op, when we want to represent it in pseudo C code, is just open and close brace. What does that do in the C program? Come on, you guys know C, right? So what happens when you have this in the C program? Open and close brace right away. It's an empty scope, but in terms of what it is going to do, that would be absolutely nothing. Okay, it's not going to do a single thing, and that's exactly why it is no op, because it doesn't do a single thing. The only side effect of no op is the program counter advancing to the next location. Other than that, it did not read anything. It did not update anything other than the program counter. It did not do any calculation. It didn't do a single thing. That's why it's called a no op instruction. The semicolon is, I prefer not to use the semicolon because the semicolon is more syntactical than it is semantic. So that's why I do not use the semicolon. All right, so now we are done. Okay, now we are done with today's lecture because we have now talked about an entire instruction cycle: fetch, decode, execute, do whatever the opcode wants us to do. Then we go back to fetch again. Okay, so all of that stuff is important. So now it is time to go take a look at the next lab, and I want to see if we are ready to open it. Okay, so it's this one here. And I'm just going to take a quick preview of the questions. All right, so I think we can do this one. Question 1 for sure. Question 2. Okay, so I do need to explain what is a slice. A slice is nothing more than a location in ROM. So whenever you see the term slice, it really just means a location in ROM. That's all it means. All right, so let's move on. One is about the address, the other one is about the content at that address. Okay, moving on. Okay, so this one has to do with how many ways, what is the number of individual opcodes in a family of opcodes? Okay. The question 5 is about labels. All right, maybe not tonight. Okay, so I'm going to withhold this lab until Thursday, because on Thursday I will talk about the use of labels just a little bit, just so that you guys would have everything that you need to get this lab done on Thursday. It does not mean that there's nothing to do today, because I think what I have just explained today is quite a bit already. Okay, so it's going to take some time to sink in, so you might want to listen to the lecture again, but this time, use the pause button more often to absorb the content. Okay. Okay, I'm just looking at the text here. Yes, so I do want you guys to have time to absorb and make connections between the concepts. All right, cool. All right, so I'm just going to type here, no lab tonight. All right, there we go. Okay, so you guys got some stuff to do. At this point, studying is a little bit different. There are very few modules at this point, because the okay, I'll put it this way. I know we are over time already, but since this is technically the lab time and people are supposed to have allocated the time for the lab, I can kind of abuse that a little bit. So the instruction is all buried within the processor design itself. In other words, this is your module. This is the thing that you need to read and understand. Now, doing this statically is not going to do you a lot of good. It will do you some good, but not a whole lot. So repeating what I just did using the Control T mechanism to try to figure out what is getting updated, how it is updated, and how components are connected through the multiplexers and the demultiplexers, that is important. Okay. Tom has a request of a. Okay, yeah, we can do that. I have office hours from noon to 1, so if you direct message me, during that time, we can do it. Or anytime that you find me online, you can just direct message me to arrange for a one-on-one office hour, so that's fine. What was I talking about? Oh, right. So the other thing that you guys might want to do is to go through the opcode table and pick another one to single step through, okay? And personally, I would pick this guy over here, not the no op, but the next one. It's called a halt instruction. And when you look at the C notation of the halt instruction, it's like, what is that? It's an infinite loop. Okay, it's a loop that you cannot get out of. Okay, once you get to the halt instruction, you are now stuck at the halt instruction. So this would be the next one that you can single step through in order to understand why once you get to the halt instruction, you're stuck. Okay, so I would definitely pick this one as the next one to play with, because it does not depend on what you put into registers. It doesn't have any type of indirect addressing and stuff like that. So I would definitely try this one as the next instruction that you can go through single stepping by yourself. And Tom, if you want to, I do have time, kind of right after the lecture, so that works for me too. All right, so I think now is the time for me to stop. Okay, so we're just over by what, 20 minutes? No, 25 minutes. That's not too bad. Okay, so I am going to stop lecturing and stop the screen share and the streaming. All right, I'll see you guys on Thursday. So study hard, just kind of try your best to understand how the processor works.